Okay, fasten your seatbelts because this Monday morning review is full of proper, good old-fashioned software drama. Yes, we need to discuss the ban rewrite because beneath all the blog posts and Twitter opinions, there are some really valuable lessons for people involved in software in 2026. For those living under a rock, or for those smart enough to avoid JavaScript development in general, Bun is a JS runtime built as an alternative to Node. They famously decided to use Zig, which is a language still under heavy development by the way, because it offered low-level control, great C interoperability, and the ability to build an extremely fast standalone executable. The experiment clearly worked, Bun gained immediate recognition, and investors were eager to back what appeared to be a promising open-source project. But fast forward a couple of years, and at the beginning of 2026, Bun, which grew to be loved by the community, announced they'll be acquired by one of the most likable AI CEOs, who clearly has the best intentions for software and open source. Then, one of the first things the Bun team did was to use an army of agents to rewrite 500,000 lines of Zig code into Rust. And this is where the whole drama started. To be fair, Bun's official explanation for the rewrite is actually pretty reasonable. Bun lives at the intersection of two very different memory models. JavaScript Core, the engine behind Safari and Bun, uses garbage collection, while Zig gives developers direct control over native memory. Connecting these two worlds means Bun constantly has to track which JavaScript values are still alive, which native objects own which pointers, and who is responsible for cleaning everything up. As Bun grew, this became a recurring source of use after free bugs, double freeze, and memory leaks. The team already used address sanitizer, safety-checked builds, leak tests, and continuous fuzzing, but they were still fixing memory-related bugs on a regular basis. So in their opinion, Rust offered a real technical advantage. In Zig, memory cleanup is explicit. You usually allocate something and then use defer to make sure it gets released when the current scope ends. This is simple and predictable, but the developer still needs to add that cleanup at every relevant call site and understand exactly who owns the memory. Rust moves more of this responsibility into the language. Its ownership system tracks who owns a value, the borrow checker controls how references are used, and automatically runs the cleanup logic when a value goes out of scope. This means many use after free bugs and double freeze become compiler errors instead of production incidents. So, despite all the language war content currently being created, Rust is probably a better fit for the specific problem Bun was facing. Note that I am not arguing that one language is better than the other. In my opinion, language wars are stupid because there are usually tailored solutions for specific problems. Of course, JavaScript is the only exception here, since it was proven time and time again that JS is the language best suited for anything ranging from machine learning to game development. The problem is that Bun contained more than 535,000 lines of Zig. According to Jared, manually porting that code would take 3 experienced engineers around 1 year, during which the team would struggle to ship features, improve Node compatibility, or even fix bugs in the existing version. But Bun now works for an AI company, so instead Jared decided to spend 1 week finding out whether Claude could rewrite the entire thing. And, to be fair, the process they built is worth studying, because I do believe a lot of similar software rewrites will happen in the future. They first used an LLM to create a detailed porting guide describing how common Zig types and patterns should be represented in Rust. The agents also analyzed the lifetime requirements of Bun's data structures and stored the results in a large table. Then, around 50 automated workflows started running continuously. Some workflows translated Zig files into Rust. Others fixed compiler errors, ran tests, reviewed changes, or refactored the generated code. At peak, Bun was running 64 Claude instances at the same time across 4 separate Git worktrees. Each batch of code was produced by one agent and reviewed by at least 2 separate agents, instructed to assume the implementation was wrong and find reasons why it would fail. At peak, Claude generated around 1,300 lines of code per minute, and, of course, initially absolutely none of it worked. The initial port produced around 16,000 compiler errors, and the team used those errors as a work queue, dividing them by crate and sending more agents to fix them. What's interesting is that agents occasionally try to cheat by replacing broken implementations with stubs, so Jared had to update the workflow to reject those changes. After the compiler errors were resolved, the agents moved through smoke tests, local tests, and finally Bun's complete test suite across Linux, macOS, and Windows. In total, the rewrite took 11 days, produced 6,778 commits, and landed more than 1 million added lines. It consumed roughly $165,000 in API usage at public prices, although Anthropic charging Anthropic for Claude tokens is probably a slightly different economic calculation from the one available to the rest of us. Ban says that the current version 1.4 fixes 128 bugs that can still be reproduced in the final Zig release. The Zig version reached around the 6.7 GB of memory because every build leaked roughly 3 MB. The Rust version stabilized at around 600 MB. The binary became roughly 20% smaller on Linux and Windows, and Ban's benchmarks show performance improvements between 2 and 5%. Around 4% of the Rust code currently remains inside unsafe blocks, mostly around JavaScript core and other C and C++ libraries. So, case closed. Rust solved the bugs, AI rewrote a project in 11 days, software engineers can finally start preparing for their new careers as Uber drivers. Except the day after Ban published the article, Andrew Kelly, the creator of Zig, released a response which can most accurately be described as choosing violence. Andrew explains that the relationship between Ban and the Zig community had been deteriorating for years. According to him, Ban moved extremely fast, accumulated technical debt, and repeatedly ignored advice from the Zig Software Foundation. He describes the codebase as hacks built on top of more hacks and says Jared was writing slop long before LLMs arrived. His main argument is that Ban's article presents a false choice. Either you rely on a style guide and hope developers correctly manage memory, or you switch to Rust and allow the compiler to enforce ownership for you. But there is a third option where you dedicate engineering time to designing clear memory rules, reviewing code, and systematically eliminating bugs. Andrew points to Tiger Beetle, another major Zig project, which follows an extremely strict engineering philosophy called Tiger Style. Among other things, Tiger Beetle allocates its memory at startup and avoids dynamic allocation while the system is running, removing entire categories of memory bugs through architecture rather than language enforcement. Tiger Beetle's architecture is deserving of a video on its own, so please let me know if you are interested in it. Of course, Ban cannot simply copy that approach. A JavaScript runtime has very different requirements from a financial database. But Andrew's broader point still stands. The problem is not that Zig is making reliable software impossible or really hard to achieve. It may just be that Ban's culture prioritized shipping features over spending the time required to use Zig safely. Zig's creator also identifies a rather interesting contradiction in the AI story. Ban argues that it was safe to merge more than 1 million lines of generated Rust because its test suite was comprehensive enough to verify the rewrite. But if the test suite is capable of validating 1 million lines of AI-generated code, why was it unable to prevent all the bugs in the original Zig implementation? Either the test suite provides enough confidence for such a rewrite, or it does not. Using it as proof when defending the Rust port while blaming Zig for bugs it previously failed to detect is at least convenient. The performance claims also deserve more context. Ban attributes part of the speed improvement to cross-language link time optimization between Rust and its C and C++ dependencies. Andrew points out that Zig has supported LTO throughout Ban's existence, so this was an optimization Ban could have enabled before rewriting the project. Similarly, the 20% binary size reduction combines several different changes. Some savings came from removing Ban's excessive use of Zig's comp time, but others came from stripping unused ICU data, compressing parts of ICU, and enabling identical code folding at a linker level. Those are useful improvements, but they are engineering improvements performed during the rewrite, not automatic properties of Rust. Andrew also noticed that Ban's long article contains benchmarks for runtime performance, memory usage, and binary size, but says nothing about compilation speed. Rust is famous for many things. Fast compilation is typically not one of them. Trading slower builds for stronger memory safety guarantees may be completely reasonable, but when a technical migration presents only benefits and conveniently forgets the cost, it starts giving kind of a biased vibe. Ban had a legitimate memory management problem, and there were several possible solutions. They could improve their engineering process, introduce stronger ownership conventions, continue fixing bugs incrementally, or rewrite the project in Rust. But only one of those options allowed Anthropic to publish a story about its new model, rewriting 500,000 lines of production software in 11 days. The Rust rewrite may have been the correct technical decision, but it was also an almost perfect marketing demonstration for Claude. Anthropic already uses Rust, the Zig community is openly hostile toward dumping unreviewed AI output into open source projects, and Ban now exists inside a company whose valuation depends heavily on convincing everyone that AI can replace increasingly large parts of software engineering. So the results might not be fake, but Anthropic is definitely not a neutral narrator. The most useful lesson here is that programming language choices have to match the team that will actually use the language. A disciplined team with strict architectural rules can build extremely reliable software in Zig. A fast-moving product team working across garbage-collected and manually managed memory may benefit enormously from having Rust's compiler enforce ownership rules. So you should always choose technology for the real needs and capabilities you have. The second lesson is that AI changes the economics of rewriting software. A migration that would never survive on normal cost-benefit analysis can suddenly become possible when agents perform the mechanical translation. But this worked because Bun already had an architecture, a porting guide, compiler feedback, millions of test assertions, sanitizers, fuzzers, adversarial reviews, and one engineer continuously supervising the process. Claude generated the code. The surrounding engineering system turned that output into software. And the final lesson is that when you change the programming language, memory model, compiler settings, linker configuration, testing strategy, and development process at the same time, you cannot honestly attribute every improvement to one variable. The reality is that Bun finally dedicated an enormous amount of compute, tooling, and engineering attention to problems it had accumulated over several years. And, apparently, the most reliable way to get a Silicon Valley company to address its technical debt is to convince the managers that fixing it will make a good AI demo. Please don't forget to like the video, subscribe to the channel, and, until next time, thank you for watching.